Hello everyone, and welcome to the online session for applied thermodynamics. Today I'm going to talk about chemical reactions, which is last chapter or last topic for your course. In this chapter we are going to see what are fuel, what is combustion, how to use the law of the mass conservation to evaluate the combustion or reactions, and also define some parameter for the combustion analysis such as air-fuel ratio, percent theoretical air, or dew point temperature. And also we will see how to apply energy, how to apply energy balance for the reacting system to have for the both steady flow control volume and also fixed mass system or closed system. And also we calculate the enthalpy of reaction, enthalpy of combustion, and heating value of different fuels. Moreover, we will determine the adiabatic flame temperature, which is an important parameter with different fuels, especially when for designing of the medium which those fuel are going to be burned in those devices. And also we will evaluate the entropy changes for different reacting systems. And finally, we will analyze reacting system from the second law of thermodynamic perspective to see how much is what is irreversibility of these reactions. Okay, let's see what is the differences and similarity in this chapter with the previous chapter. Up to now we have considered different systems which include changing energy in thermal energy of those systems, but those changes was mainly due to the change in the state of the system. In this chapter we are going to see another reason for the change in the energy of the system, which is the change in the chemical energy of the system. Actually, chemical energy of the system is the energy between which is now already between the molecule or atoms for the material. By releasing this energy, some changes in the system can be evaluated or can be seen. Let's start with some definition. Fuels are any material which can be burned to produce or release thermal energy. So you may have experience with different kind of fuels, but main fuels consist of hydrogen and carbon, that we mainly call them hydrocarbon. Hydrocarbon like gasoline, like methane, like different kind of the material which can extracted from the oil are mainly hydrocarbon fuels. And their general formula is, as you can see in this here, is C down N, H down M, which N and M is the number of the atoms of the carbon and hydrogen for that kind of fuel. And these hydrocarbon fuels actually can be seen or can be found in all phases. Some of the example for different phases, for the solid phase is the coal hydrocarbon, which is one kind of hydrocarbon. Gasoline is liquid one, which also can be called octane or C8, as you can see here, C8H18. And also for the gas phase, we have natural gas, which is also hydrocarbon fuels. All of these, most of the fuels, like gasoline and natural gas, are the result of distillation. By distillation of crude oil, as you can see in this figure, result of distillation of the crude oil can be gasoline, kerosene, diesel fuel, and also fuel oil. Different kind of hydrocarbon fuel can come from the crude oil. And also the characteristic of this fuel is different. In next slides we will see what is the difference between different kind of fuels, but usually the energy content of this fuel is different. In other words, how much energy in terms of kilojoule can be is released per liter. As you can see here, it is different for different fuel. For example, for gasoline, the energy content is 31,000 something, but for light diesel, it's low. It's higher. It's 33,000 something, and for heavy diesel, it's even higher. And usually we call for simplicity, we compare the energy content of different fuel with gasoline, as you can see here. But what is really a combustion reaction? Combustion reaction is a result of a reaction between the fuel and air, and we call this process sometimes oxidation. And oxidizer is mainly air. And why air? Because air can reacted with most of this fuel, and also air is highest substances in the environment. Its availability is higher than any other material. Then, but what is the air? Air, in terms, if we consider a mole, or in terms of volume basis, we evaluate air, we will find out that about 20.9% of the air is oxygen molecule, about 78.1% is nitrogen molecule, and 0.9% is argon. And it is also include small amounts of carbon dioxide, helium, neon, and also hydrogen. But for our analysis, we assume that the dry air is approximately consists of 21% oxygen and 79% nitrogen by mole numbers. It will simplify our calculation, and it's better to have this assumption. Combustion also can be defined like what you can see here, is a chemical reaction which during that a fuel is reacted with the air and huge amount of the energy is released. So because of that we are interested about combustion, because with the energy density of the fuels, it's very high, and we can earn lots of energy due by the combustion. And as I said before, the air is about 79% nitrogen, 21% oxygen. In other words, for 1 kilomole oxygen molecule, we have about 3.76 kilomole of nitrogen molecule. And totally we have 4.76 kilomole air. However, the combustion is a result of the combination or reaction of the fuel and air. We usually need some situation or condition to have combustion. First, the fuel should be above its ignition temperature to start the combustion. in another case, we can see the combustion all over around us, because many of the fuel now are in contact with the air, but the temperature is not that much enough to start the combustion. So this ignition temperature is the minimum ignition temperature which starts the combustion or reaction between the fuel and the air. And this ignition temperature for different fuel are mentioned here. For example, for gasoline, the ignition temperature is about 260 degrees Celsius. For carbon, it's 400 degrees Celsius. For hydrogen is 508 degrees Celsius. For carbon monoxide is 610 degrees Celsius, and for methane is 630 degrees Celsius. So this is first condition to start the combustion reaction. We need to have temperature above the ignition temperature. Moreover, we need a specific amount of fuel and air to have a combustion reaction. For example, natural gas does not start to burn in air if the concentration of that is less than 5% or greater than about 15%. In other words, we need a specific amount or proportion of the fuel and air to start the combustion reaction. A combustion reaction is actually a reaction between the reactants to produce products. The substances which are in the before the reaction are mainly called reactants, and the substances which are formed after the reaction are called products. For example, as you can see here, we have a reaction here. Carbon is reacted with oxygen, and the product is CO2. So in this reaction, CnO2 are reactant and CO2 is the product of this reaction. And one more important thing is about the mass balance between the reactant and the products. According to first law of thermodynamics, you know that there isn't any mass loss during any reaction. So also for combustion reaction, the number of atoms in the reactant site should be equal to number of atoms in the product site. So we will use this concept to write the equation or the reaction for different fuels. As you can see here, for example, in the reaction of hydrogen and oxygen, the water is produced, but you can see the number of the molecule in the left side of the reaction is equal to right side of the reaction. Two hydrogen, two molecule of hydrogen at the left side, two molecule of hydrogen at the right side, and also just one molecule here. We call this molar value. So when we have O2, it means that we have two molecule here, and but it is multiplied by 1 by 2. So 1 mole of oxygen will be here, so we will have also 1 mole of oxygen molecule at the right side, or products of this reaction. And in terms of molar mass, we can also define this molar mass of the hydrogen is 1, and for oxygen is 16. So again, we can compare the molar mass of the different molecule, different substances, the reactant and the products. But the total number of moles is not conserved during a chemical reaction. So the mole can change, but the mass should be same at the both sides of the reaction. One more important thing about the combustion is the air-fuel ratio. As I mentioned before, combustion is a result of a reaction between the air and fuel. And also the combustion will start when the specific proportion of air and fuel are mixed or reacted or are mixed. So we can define the air-fuel ratio as a parameter to know if enough or appropriate mass of air is combined with the mass of the fuel. So air-fuel ratio is the mass in terms of mass basis, and it is defined as the ratio of the mass of the air to the mass of the fuel for a combustion process. In other words, AF is equal to M of air, M of to the by M of fuel. To have the mass of air and mass of fuel by their molar mass, we can use this equality, this equation. The mass of air or fuel or any other substances is equal to number of moles of that substance, times the molar mass of that molecule or substances. And the reciprocal of air-fuel ratio is called fuel-air ratio. It is also can be used to define this ratio between the fuel and air. And here you can see an example. 1 kg of the fuel is reacted 117 kg of air to produce 80 kg of the product, and you can see the mass conservation 18 kg for reactant and product, and also the air-fuel ratio is 70 mole, kilomole, and or kilogram for 1 kilogram fuel. We have 70 kilogram of air to react with 1 kilogram fuel. Here we have an example to balance combustion equation. We will use the concept of mass conservation to write the equation for the combustion. Here we have 1 kilomole of octane, which is its molecular structure or molecular formula is C8H18. It is burned with air that contains 20 kilomole of oxygen, as shown in this figure. You can see here 1 kilomole of the octane is reacted with air, which the air is 20 kilomole. Then assume the product contains only CO2. The reactant are CO2, H2O, O2, and also nitrogen molecule or N2. We don't know how much is the mole or the amount of each one of these molecules. Okay, now how we can write the reaction equation. Okay, now let's see how we can solve this problem. How to balance the combustion equation for this octane as a fuel, which is reacted with the air, which contains with the 20 kilomole of the oxygen. And the product are CO2, H2O, O2, and nitrogen. We know the mole of the octane and also the air, but we don't know the mole of CO2, H2O, O2, and N2. Okay, first let's start with our assumptions. Okay, so first of all, we know only as a reactant are only H2O, CO2, O2, and N2. And from table A1, we know about the air, which its molar mass is 28.97, or approximately 29 kilogram per kilomole. Okay, first write these reactants and the product in the equation. You have C8, this fuel, which is reacted with 20 mole of the air. As I told you, air is contain oxygen plus nitrogen. This relationship I already introduced to you. The air is okay, sorry, let me just write this 6 nitrogen. As I told you, in each mole of the air we have 3.76 mole nitrogen and 1 mole oxygen, so we have 20 mole of the air, and we should write like this. And the products are CO2, water or H2O, oxygen, and nitrogen. But we don't know their amount, so we are going to find the value for these products. We just write like this. But according to the conservation of the mass, we know that the mass for the molecule or atoms in the left side of this reaction should be equal to the number or the mass of the atoms in the right side or in the products. So we can write like this. For carbon, we have, you can consider here, we have 8 atoms of carbon here. What about products? As you can see here, only for the carbon dioxide we have carbon and so X will be 8. What about hydrogen? As you can see here, we have 18 hydrogen. So 18 atoms of hydrogen in the reactants. What about products? As you can see here, we have H2 only here. So this should be written like this: 2y. Y multiplied by H2 should be equal to 18 number of atoms for the hydrogen. So y will be 9. X is 8. Okay, then what about oxygen atoms? As you can see here, how many atoms we have here? 20 times 2. 20 times 2 atoms for in the reactant side. What about the products? We have 2x plus here 1y plus, what about z? We have to z. We already know how much is X, how much is Y? So Z will be 7.5. What about N2 or nitrogen? We should write the mass conservation for nitrogen. How many atoms of nitrogen in the reactant sites? 20 times 3.76. So we can write that 20 times 3.76. So as we have N2 inert or intact in both sides of this reaction, we can just write like this: to 20 times 3.76 equal to W. So W will be 75.2. Okay, now we should substitute the values to rewrite the equation. We should write C8 H18, the mole was 120 O2 plus 3.76 into. Then by substitution of the X, Y, Z and W, we will have this equation: 8 CO2, X was 8, plus 9 H2O plus 7.5 for oxygen, O2 plus 75.2 into. So this is the combustion reaction, combustion equation for the methane, and 20 kilomole of the air. Okay, next we are interested to calculate the air-fuel ratio. As you may remember, we had this equation for air-fuel ratio. We should find the result of this equation, the mass of the air divided by the mass of the fuel, which is equal to the molar mass of the air times the mole of the air divided by the molar mass of the fuel, which here is carbon plus hydrogen or H2. Okay, now to calculate this, we should substitute the value for molar mass of the air, molar mass of the carbon, molar mass of the hydrogen, substitute in this equation. So this will be equal to 20 molar mass of the air times 4.76 kilomole times 29 kilomole. This is molar mass of the air, as I mentioned as the properties. Then what about the fuel? As you can see here, fuel is consists of carbon and hydrogen. We should have the molar mass of carbon and hydrogen. So for carbon, we have 8 atom of carbon, so 8 kilomole times the molar mass of the carbon is 12 kilogram per kilomole plus What about hydrogen? Hydrogen usually is H2 in the environment, so we can have the molar mass for H2, which is 2 kilogram per kilomole. So by substitution, we have 9 kilomole of H2, which its molar mass is 2 kilogram per kilomole. So this air-fuel ratio will be equal to 24.2 kilogram of air for kilogram of fuel. In other words, we need 24.2 kilogram of air to react with 1 kilogram of fuel.